So yeah, for those of you who've been following, you'll be aware that we've been kind of working a little bit on ultrasound for a while now, but essentially we've kind of wrapped up a significant amount of that work, and so this is just to kind of give it an overview of what's available today for people to kind of work with and build on if they're interested, and kind of go through that. So going back to kind of why we did this in the first place, as kind of a reminder, ultrasound is a really nice fit, almost kind of weirdly well for Monty for a number of reasons. So one is it's an inherently sensory motor form of inference and kind of learning that a clinician does when they move the probe over a patient and see what's there. Um, but of course, it has real world kind of applications as well. And importantly, those are also generally small data. So any kind of healthcare setting in general, you don't have much training data. That means many existing approaches aren't going to work well. And that's, of course, where Monty tends to shine. Um, and there's also this kind of natural mechanism for enacting motor output. So often when we've talked about a real world application like robotics, that introduces these challenges of like, okay, Monty wants to move somewhere in the world. Now something, often we talk about a subcortical structure in the brain, figures out how to move there. But it's quite easy to kind of conceptualize how ultrasound could be set up in such a way that a trained operator could kind of manifest the movements that Monty wants to achieve. Um, and just kind of as a brief reminder in terms of ultrasound, so you have this sensor that's emitting this ultrasound wave and reading the information that's coming back, and that creates this 2D image that's a slice through a 3D structure, and that 2D plane is moved around as the kind of operator visualizes whatever the structure is. Um, but it can be challenging to interpret. So, for example, the TBP mug, if you kind of do a slice through like this, so what you see is something like this. So this is kind of a cross section of the handle, and this is the side of the mug. You see the curvature there. But ultrasound is associated with lots of kind of artifacts and things that you kind of need to get used to dealing with. So, for example, if a sound wave gets reflected too early or too late, you can kind of have hallucinated features in space, but you can also get acoustic shadows if the waves are blocked entirely, and so on. Um, and in terms of, yeah, just real world applications to make that a bit more concrete. So it's one of the main focuses actually of the Gates Foundation, who's one of our funders. And around two-thirds of the world's pregnant women don't have access to ultrasound, even though it can be a life-saving intervention in terms of recognizing maternal and kind of fetal issues, but it has other applications as well, including things like infectious diseases and trauma. And so it would be amazing if this technology could be made available more broadly. But of course, we need a solution. I said healthcare data tends to be small data, especially if you're talking about pathology. And of course, in a setting like this, you want it to be interpretable. And the kind of current state of the art leverages deep learning approaches. But because of a combination of kind of the amount of training data needed and the kind of limitations in terms of adapting to whatever is being sensed, they rely on this kind of blind sweep paradigm where basically operators are trained to perform a series of kind of stereotyped sweeps over the belly. And then this is always done. But if you actually see a trained sonographer work, you'll see that they adapt the position of the probe to the patient and to the setting. And this is really important for getting good quality views because everything from bowel gas to bones to various other anatomical features can compromise the quality of the view. And so this is quite a kind of crude workaround. And in general, for kind of the maybe simplest medical measures, there's been some benefits from kind of using this, but in general, this is limited in terms of the kind of diversity of clinical outcomes and kind of measures that people want. So of course, enter Monty. And if you're watching this and are first learning about its capabilities, definitely recommend checking out this paper. But essentially, Monty, can learn continuously and rapidly from small amounts of data. The models it represents are it learns are structured in a way that makes them interpretable, and it can propose actions for where to move in the world. And as I kind of alluded to earlier, we can imagine setups where a human operator could actually kind of carry out these movements and just like a trained sonographer would actually move to where would be a better view. And so in terms of kind of ultrasound in Monty, this all began back in May last year, where we kind of had this proof of concept that we could collect data, including importantly where a probe is as we're kind of scanning objects. And at the time, we could kind of pretty inconsistently perform inference. The kind of whole pipeline was working, but we weren't really getting the results we wanted. And you can maybe see from the model here that was learned that the results at the time were quite noisy. So we're not getting kind of really the outline of a spam can like we would hope. Um, and so what's happened since then is we've scanned a data set of 10 objects. So rather than just kind of one or two objects. So 10 objects and done this with a refined pipeline so that we have much less noisy data. This was, yeah, a variety of kind of changes, but you see that here much more closely matches the outline of the spam can. Um, and this kind of the repository needed for running simulations with this data set and the data sets themselves are kind of now ready to use and experiment with. And I'll show some benchmark results later that look at both kind of sim to real and real to real. And what we're really looking for is ways that we can now kind of improve performance. And so we've documented some kind of open issues that we think would make a big difference. And the hope is, if you're watching this and you're part of the community and you're interested in either kind of real world applications of Monty or medical applications, or just kind of seeing what it's capable of, then you might be interested in kind of taking on some of these issues. And so, yeah, I said kind of performance is now better with this new data set, but there's lots of ways that we can make it even better. And so after this, we're going to be sharing the repository through our various kind of channels. And then we have some industry partners that we've been collaborating with on and off. And so we think they'll also be interested in kind of playing around with this data set. And by industry partners, I mean both people who kind of produce types of ultrasound probes, as well as teams that kind of set up pipelines, for example, to deliver ultrasound in resource poor settings. So just kind of a recap on the kind of setup, either if you've not seen it before or since it's been a while. Yeah, we go into more detail from our hackathon presentation from May last year. And also in the repository documentation, there's lots of details. But essentially, we have this probe that's going to be collecting images, and the kind of initial image would look something like this in the case of the spam can. So you see, if you imagine kind of a cross section through it, you see the wall of the can here. But because it's Monty, we're interested in a morphological feature at a pose. And so we extract that by kind of doing some analysis on an image patch where we think there's an edge. And that gives us, essentially the presence of an edge, its orientation given by this kind of surface normal, and the curvature associated with that edge. And then at the same time, as we kind of scanned the objects, we were tracking the position of the probe, and we did this with essentially a setup that is designed for virtual reality, but which we could co-opt for our kind of setting here. And that tells us that at a very high rate, like kind of 100 hertz, much higher than we need, where the probe is in space while we're doing the scanning. And then we also had a kind of phantom setup. And so this is what we were actually scanning. A phantom often refers, in a medical setting to something that kind of mimics, for example, a fetus in a uterus being scanned. But in our case, it's 3D kind of everyday objects. And so that's spam can, ripper heart, things like that, suspended in fluid. And then the probe is put on the outside of this bag with some ultrasound gel on the front. And so there's essentially a constant fluid connection, or certainly no air gap between the tip of the probe and then whatever object is being scanned. And then as you kind of move the probe, you get a bunch of images, and within those images, these patches that I was referring to earlier, and those are going to be the kind of feature at a location, feature at a pose that we're extracting, and then through those and through the movement information that it's receiving, Monty then learns and builds up models of these objects and then can do inference. Um, and so, yeah, I won't go through kind of the full pipeline here, but essentially the information about the tracker and the images was being sent to a variety of things, including iPad and a Windows machine. All this was being kind of integrated in real time, and this was necessary to collect the data. The good news is this is all done, and so now you can just download the data set, which has these paired ultrasound images along with the tracking data, and then you can both do learning with Monty on those as well as see how it does at inference. And so an example of kind of the learned model that it would develop now for something like the rubber heart is what you see on the left. And so, yeah, I said the repository is public now and is also should be kind of easier to use in terms of the documentation and also all the kind of download links and everything being there. And I'll go to it in a moment. But then the kind of data set, just to give a bit of context, essentially we have 10 objects. 6 of those were from our first real world hackathon. If you followed that, that was called Monty Meets World, and that was using an iPad with the kind of depth camera that it has. And then 4 objects from the YCB data set. And the reason for the mix is because there were some objects in this first one that were very stubborn when it came to sinking or kind of staying in water. And so they would pop out and yeah, but you have to have stuff submerged in order to scan it in ultrasound.
Well, one of them was also a book, so we wouldn't want to put it into water.
Right. Yeah, one of them was a book. So yeah. And this is showing the 3D scans of these objects. So one of the important things that you'll see with the kind of repository and the setup is that one way you can train Monty is in simulation and then see how it does with the ultrasound data. And then I've shown a couple examples like the spam can and the heart, but this is just showing more of the kind of learned models that Monty develops. If you kind of study them, you start to kind of see the shape, and I've kind of oriented these objects alongside to help you kind of see that. But as I'll get to with the issues, one of the problems you might notice quite quickly, for example, is these sort of anomalous points, like you see here with the hot sauce bottle. Like this is clearly the outline of the bottle, but for some reason, Monty has learned some points all the way over here. And that could be a variety of things. That could be noise in where the tracker thinks it is in 3D space, or it could be noise or kind of errors within the kind of ultrasound plane where Monty thinks that there is an edge and where it's kind of marked that location, or it could be a combination of those. So that's one of the things that we want to address is these kind of anomalous points. And then this is just showing, so we have kind of two data sets. So the ones that are generally designed for learning consist of 200 data points per object. And so this is kind of a dense scan where we tried to systematically cover as much of every object as we could. Including sort of characteristic features like the handle in the case of the coffee mug, or these kinds of the sort of aorta coming out and things like that in the case of the heart. You'll notice in some instances, like the mustard bottle, why is it kind of empty over here? Basically, the mustard bottle is quite a large object, and the way it's sitting in space and the realities of that plastic bag you saw, it wasn't always possible to get a view of an object from every angle. And again, that actually fits quite well with the realities of medical ultrasound. If you're scanning a kidney or a fetus or whatever it happens to be, often there's a few kind of characteristic views you can get of what you're interested in, but you don't have the luxury of a kind of 360-degree view of everything. But that's one of the interesting challenges of, I guess, this benchmark and this data set. But as you can see, yeah, that one's quite systematic. And then we also have this data set where there's 50 scan points rather than 200 for every object. So in addition to there being fewer points, a different kind of policy was used by the scanner as they went over the object. So with this one, we just kind of systematically went around. With this one, the idea was to kind of move quite quickly from sort of one interesting part of the object or one kind of side of the object to another, to kind of model the idea of trying to basically infer the object as quickly as possible. But you can see it's much harder, even for a human, to kind of recognize what the objects are from these. And so in terms of our performance today, so there's three main benchmarks. There's reel-to-reel, sim-to-reel with sparse inference, and sim-to-reel with dense inference. So reel-to-reel is where we are training on these, on the data sets that basically result in these learned models, and performing inference with this data set. And we get a pretty decent 80%. And also taking an average of 24 steps, so not needing to use all 50 of those available data points. Um, but of course, 80% isn't 100%. So one thing we'd like to do is kind of improve that performance and get the correct classification on all of these. But the one where we're imagining seeing particular gains is on the sim to real. And it's important to note for sim to real. So what I mean by that is that's training in simulation on these. So on kind of 3D scanned objects that are essentially kind of RGBD, and performing inference based on this kind of input, so ultrasound. So it's not just going from, because there is such a thing as like simulated ultrasound, where people will kind of simulate what a heart or whatever structure looks like in ultrasound. Um, that's not what we're doing here. So it's not only is it a kind of transfer from simulated to real data, it's also a modality shift from RGBD based inputs to ultrasound based inputs. Um, so with that kind of context, I think the performance isn't too shabby as a starting point, in terms of, so the two kind of settings here are where we train on those simulated objects, and then we either do inference on these ones, so where we have the luxury of all 200 kind of data points, or on this more challenging kind of sparse subset. Um, but there are a variety of kind of key things where it's not too surprising that we're seeing this performance right now. As said, there's these things like these anomalous kind of points and things like that we want to address. But essentially, boosting the accuracy on all of these benchmarks and also getting the number of steps down for these two is what we're aiming for. We could also explore that with this one. For the moment, we actually set the number of steps here to 200, because this is kind of trying to get a measure of, okay, assume essentially unbounded access to the ultrasound scan. How does Monty do? Um, and so, yeah,
And that's still with, like, for example, the mustard bottle mesh is a different size than the physical
exactly.
mustard bottle we used for the ultrasound images.
Right,
Yeah,
exactly.
things like that.
Yeah, so this is the repository, um, uh, which yeah, goes through uh, all the kind of how to basically get set up. It's pretty quick. You can both download the pre-trained models if you just want to use them out of the bag, or you can retrain them yourselves. It only takes kind of a few minutes, or maybe like half an hour, but it's not a particularly long process. Um, And if you are really keen, we have still documented how we originally collected this data set. So, say you're a research group at a university and you want to collect a similar data set or expand it, there are instructions for how we did that. But the real focus for the repository today is to basically see what we can do to experiment with inference and learning with Monty and get this kind of performance improved. Um, and on that note, then, yeah, I said we have kind of a number of open issues, and I'll just kind of highlight a few of them. Um, so, this bar always gets in the way. Yeah, probably the biggest one is to get TBP ultrasound perception. This repository to use the latest version of tbp.monty. So right now we're tagged to an significantly older version of tbp.monty, basically a year old. And that means that all the kind of new algorithmic improvements that we've made are not accessible when doing learning and inference in this environment. And so this would be a pretty meaty change, but when kind of someone did this, it would unlock lots of new features that are currently available, like burst sampling, the kind of feature that Rami had implemented, which should help us deal with a lot of that real world noise. Um, But also, once we have it up to date, then we can also look at, trying to maintain compatibility with the latest version of TBP.Monty. And that means that any kind of future features that we implement, and the ones that are described in our future work section on the readme.com, then we would also see how those impact performance here. Uh, and then there's some kind of more specific ones. So, for example, in in Monty right now, in YCB with the YCB objects with the RGBD input, we're already looking at exploring extracting better non-morphological features. So that is kind of, if something is kind of furry or glossy, how do you kind of represent that in a way that the model can kind of store that and then recognize that. And with our collaboration with Penn State, that's very close to being finished and implemented. Which again means that if we were on the latest version of TPP.Monty, a lot of the infrastructure for this task would be available. But the difference here is that it would be looking at this concept of echo texture, which is a very similar concept, but basically you can imagine that in ultrasound as well, different objects will have kind of different characteristic appearances. So, if you look at the edge of the mustard bottle, it has this kind of clean, sharp edge. Whereas if you look at Monty's heart, because of the kind of structure of latex or whatever it is that it's made of, it has this kind of wavy, multi-layered edge with high frequency waves. And then Monty's brain, which is some kind of foam, is again has this sort of characteristic, almost gradient as it kind of goes to black, with again a bit of kind of waviness. But this is the kind of thing that the basically local binary patterns, the computer vision technique that Penn State has been implementing for our YCB setup, could be used here as well. And so that would be pretty cool if we could get that coming in. And then just as a last example is kind of improving how we extract and localize the edge. So I kind of briefly mentioned how we get this large image coming in, and we basically look for what is the dominant edge in the center of it, and that's going to be our local feature. But I mentioned that depending on how the sound waves are reflected and delayed and so forth, you can get these additional kind of artifacts appearing, and those might be, and those can appear deep to a true edge, a true kind of in the structure of the object, or they can appear kind of superficial. I say deep and superficial because the tip of the probe is at the top here. So either they're kind of happening deep to it or superficially. And in either case, it can cause confusion about where the edge actually is in space. So you can imagine those anomalous points I was talking about earlier. If this is wildly off, if we say that this is the edge, then Monty's essentially going to learn a point at that kind of location, or it's going to, during inference, it's going to think it's suddenly at this location, when in fact it should be kind of here. And some of the work that Hojie's been doing with implementing a 2D sensor module and extracting edges in 2D images would be very relevant to improving this. And so again, if we move to the latest version of TPP.Monty, a lot of that could just be brought in kind of as is and experimented with. And then the last example is just to show that some of these are quite simple, is as Vivian was mentioning, so some of the meshes don't actually match the size of the physical objects we scanned. So if you look at the YCB dataset and the dimensions that they made public. So French's mustard bottle is sold in a variety of sizes. And this is as it turns out, characteristically American size, 40% bigger, and it's not for general sale in Europe. And so we had to buy our kind of tiny European mustard bottle and scan that one. And so they're not a perfect kind of rescaling of each other, but in general, if you were to kind of rescale the mesh, then it would match much more closely the scanned object. That's of course one solution. Another example is we have on our future work list adding scale invariance, and we have ideas for how to do that. So maybe a more long-term and kind of interesting solution to implement would actually be seeing how scale invariance makes Monty robust to that kind of transfer. But yeah, there's lots of details here. Um,
I thought
if
the one about policy was an interesting one too. Like
Oh yeah, sure.
right now, Monty basically just looks at one location in the ultrasound image versus
Right,
sonographer would usually look like saccade over the image.
right.
Um,
Yeah, I mean, maybe I'll just quickly go through all of them.
well,
Basically.
yeah, I don't have to do
I
it.
mean, yeah, it's pretty
Thought that
quick.
was
I'll just say that yeah, there's Rami's implemented this really nice TVP plot library, and so one of these future items is or issues is basically to add support for that. This is would probably be a good one to start with because it would make solving all these other issues a lot easier because you'd have these access to really nice visualizations. Um, this is the one that Vivian was just alluding to. So yeah, as mentioned, when a human sonographer looks at an image like this, they don't just do a beeline down the middle and say, "Oh, there's an edge." Um, they look across the image and then they are keeping track of, their columns are naturally keeping track of where they are in this image and integrating information there. So if we were to extract multiple edges and as well as the kind of relative positions of these, we could have much richer or much denser scans both at learning and inference. Um, and this is kind of essential for any longer term medical application because the reality is that you don't have the luxury of doing, 200 scans from 200 different locations. You might do 6 or 7 images and then integrate within those. Um, and then this is just showing some of those anomalous points that I mentioned earlier in the presentation that we want to kind of deal with. And as said, yeah, there's various possible causes for those. Um, I won't go into detail on this one. This one's a bit complicated, but basically we had to measure the distance between the tip of the probe and where this tracker was in 3D space. And every time I was doing a scan, that was basically the battery life for this probe. And the only way to charge this probe is to take off this C clamp and then yeah, basically put it. So then I of course had to try and put this clamp on as close to where it was before as possible in order to maintain that XYZ kind of offset, which I don't think I'm very good at doing, as you can see from some of these scans where there's just this kind of bias in essentially the locations of some of the points. So all of the kind of points for this wall of the tuna can are kind of over here and it's abnormally thin relative to the actual thickness and things like that. And so a lot of that is suggestive that for some of these scans, this displacement was different, and basically there should be ways that we can correct that. Um, this is again a subtle one, but yeah, it could be an interesting one. Basically checking if our surface normals were kind of mirror reversed. Um, and then this one I'll just highlight. It's kind of the one that we've emphasized as maybe a good first issue because it's essentially just updating the configs and just making sure that they have kind of the settings that we would expect for kind of good performance. And we may add to this as we kind of think of more. But yeah, if that sounds interesting, then yeah, please check it out. We're gonna be posting this on Discourse soon and YouTube. But yeah, Discourse is a great place to reach out to us if you are experimenting with this and you have any questions.